Far beyond the orbit of Neptune, drifting in the deep darkness of the outer solar system, lies one of the strangest moons ever discovered, Triton. At first glance, Triton appears to be a silent, frozen world. Its surface is covered in layers of nitrogen ice. Its temperatures plunge below minus 230 degrees Celsius, and sunlight there is more than 900 times weaker than on Earth. In such extreme cold, most scientists once believed that geological activity would be impossible. But when the spacecraft Voyager 2 flew past Triton in 1989, it revealed something astonishing. Instead of a completely dead world, Triton showed signs of active cryovolcanism, a strange type of volcanism where icy materials erupt instead of molten rock. Towering plumes of nitrogen gas were seen blasting high above the surface, leaving long dark streaks across the frozen landscape. These were not ordinary volcanoes. They were frozen volcanoes, powered not by heat from molten lava, but by pressure and volatile ices trapped beneath Triton's crust. In this documentary, we will explore the mysterious frozen volcanoes of Triton, how they work, what powers them in such a cold environment, and why this distant moon may still be one of the most geologically active worlds in the outer solar system. Hidden in the icy darkness near Neptune, Triton may be far more dynamic and far more mysterious than anyone once imagined. Far beyond the orbit of Neptune, drifting in the deep darkness of the outer solar system, lies one of the strangest moons ever discovered, Triton. At first glance, Triton appears to be a silent, frozen world. Its surface is covered in layers of nitrogen ice. Its temperatures plunge below minus 230 degrees Celsius, and sunlight there is more than 900 times weaker than on Earth. In such extreme cold, most scientists once believed that geological activity would be impossible. But when the spacecraft Voyager 2 flew past Triton in 1989, it revealed something astonishing. Instead of a completely dead world, Triton showed signs of active cryovolcanism, a strange type of volcanism where icy materials erupt instead of molten rock. Towering plumes of nitrogen gas were seen blasting high above the surface, leaving long dark streaks across the frozen landscape. These were not ordinary volcanoes. They were frozen volcanoes, powered not by heat from molten lava, but by pressure and volatile ices trapped beneath Triton's crust. In this documentary, we will explore the mysterious frozen volcanoes of Triton, how they work, what powers them in such a cold environment, and why this distant moon may still be one of the most geologically active worlds in the outer solar system. Hidden in the icy darkness near Neptune, Triton may be far more dynamic and far more mysterious than anyone once imagined. When scientists first analyzed the images returned by the Voyager 2 spacecraft, one question quickly emerged. How could a world as cold as Triton produce volcanic activity at all? On Earth, volcanoes are powered by molten rock rising from deep inside the planet. Heat from Earth's interior melts rock into magma, which then erupts through cracks in the crust. But Triton exists in an environment where temperatures are unimaginably low. The surface temperature of the moon averages around minus 235 degrees Celsius, making it one of the coldest places in the entire solar system. At such temperatures, materials that are gases on Earth become frozen solids, Water becomes rock-hard ice. Nitrogen freezes into thick layers across the surface. Methane and carbon monoxide also exist in solid form. Because of this extreme cold, traditional volcanic activity involving molten rock is extremely unlikely to occur on Triton's surface. Yet, the plumes observed by Voyager 2 clearly showed that material was being violently expelled from beneath the moon's icy crust. To understand this phenomenon, scientists began studying a different kind of volcanism, cryovolcanism. Cryovolcanism occurs when volatile substances such as water, ammonia, methane, or nitrogen behave like molten fluids in extremely cold environments. Instead of lava erupting from underground magma chambers, cryovolcanoes release slushy mixtures of ice, gas, and liquid compounds. These eruptions can reshape the surface of icy moons and dwarf planets in ways similar to traditional volcanoes on rocky worlds. On Triton, the main ingredient driving this activity appears to be nitrogen ice. Nitrogen behaves in unusual ways under the conditions present on Triton. When exposed to sunlight, even the faint sunlight that reaches Neptune's orbit can warm nitrogen ice enough to cause it to sublimate, a process in which a solid transforms directly into a gas without melting into liquid first. This process is similar to what happens when dry ice on Earth turns directly into carbon dioxide gas. However, Triton's surface contains layers of nitrogen ice that are often covered by thin deposits of darker material, possibly dust or organic compounds created by radiation. These darker layers absorb sunlight more effectively than the bright ice beneath them. As sunlight penetrates through the upper surface layers, it gradually warms the nitrogen ice below. When the ice begins to sublimate, nitrogen gas forms beneath the surface. But because the overlying layer acts like a lid, the gas cannot escape immediately. Instead, pressure begins to build. Over time, the gas accumulates in pockets beneath the icy crust. As the pressure increases, the ice above becomes stressed and eventually fractures. When the pressure becomes too great, the gas bursts upward through cracks in the surface. This eruption releases a plume of nitrogen gas mixed with dark dust particles. The plume rises several kilometers into the thin atmosphere before winds carry the material sideways across the surface. The result is a long, dark streak stretching away from the eruption site. Voyager 2 captured images showing multiple plumes in action, along with dozens of dark streaks extending across Triton's icy plains. Some of these streaks stretch more than 150 kilometers in length. The plumes themselves can reach heights of 8 kilometers or more, before being blown sideways by winds in Triton's atmosphere. This discovery revealed that Triton's surface is not static, but constantly evolving. Even though the eruptions are driven by sunlight rather than deep internal heat, they represent a powerful geological process capable of reshaping the moon's landscape. But cryovolcanism is not the only evidence that Triton is geologically active. The moon's surface also contains large regions known as cantaloupe terrain. These areas are covered in rounded, shallow depressions that resemble the texture of a cantaloupe melon. Each depression is roughly 30 to 40 kilometers wide and separated by low ridges. The origin of this strange terrain remains uncertain. Some scientists believe it may have formed when pockets of warm ice rose slowly toward the surface, creating a pattern of gentle domes and valleys. Others suggest that internal processes may have caused the surface to stretch and crack over time. Regardless of how it formed, the cantaloupe terrain indicates that Triton's interior was once warm enough for large-scale movement of ice beneath the crust. Another striking feature of Triton's surface is the presence of smooth plains. These regions appear almost completely free of impact craters. In the solar system, impact craters accumulate gradually over billions of years as asteroids and comets collide with planetary surfaces. A surface that contains few craters is usually considered geologically young. This suggests that large areas of Triton have been resurfaced relatively recently in geological terms. Cryovolcanic eruptions may play an important role in this resurfacing process. When plumes erupt, they can deposit fresh layers of material across the surface. Over time, these deposits may gradually cover older terrain and erase impact craters. This process may help explain why Triton's surface appears much younger than expected for a moon located in such a distant region of the solar system. The presence of an atmosphere also contributes to surface changes. Although Triton's atmosphere is extremely thin, only about 100,000th the density of Earth's atmosphere, it still supports winds capable of transporting dust and ice particles across the landscape. Seasonal changes on Triton may cause nitrogen ice to evaporate in one region and condense in another. This cycle can drive atmospheric circulation, creating winds that move surface material over time. Combined with cryovolcanic activity, these winds gradually reshape the moon's terrain. But the story of Triton's geological activity may go even deeper. Some scientists believe that Triton could possess a subsurface ocean hidden beneath its frozen crust. This idea arises from models of Triton's interior structure. Although the moon's surface is extremely cold, the interior may still contain heat produced by radioactive decay within its rocky core. Additionally, Triton's early history likely involved intense tidal heating when the moon was first captured by Neptune. During this period, gravitational forces between Triton and Neptune would have generated large amounts of heat inside the moon. This heat could have melted ice deep below the surface, potentially forming an ocean of liquid water mixed with ammonia or other antifreeze compounds. Over time, much of this heat may have dissipated, but some internal warmth could remain. If a subsurface ocean still exists, it might provide a reservoir of material capable of fueling cryovolcanic eruptions. Instead of simply relying on sunlight to trigger nitrogen plumes, deeper reservoirs of liquid or slushy material could occasionally rise toward the surface through cracks in the crust. Such processes have been observed on other icy moons. For example, Saturn's moon Enceladus produces powerful jets of water vapor from its south polar region. Jupiter's moon Europa may also host plumes rising from beneath its icy shell. If Triton possesses a similar subsurface ocean, it would place the moon among the most intriguing ocean worlds in the solar system. These hidden oceans have become important targets in the search for environments that might support microbial life beyond Earth. Although Triton is extremely cold at the surface, conditions beneath the ice could be very different. Liquid water mixed with chemical energy sources could potentially create environments where simple life forms might exist. For now, however, this possibility remains purely theoretical. The brief flyby of Voyager 2 provided only a glimpse of Triton's complex geology. To fully understand the Moon's interior structure and geological activity, scientists would need a dedicated mission capable of orbiting Neptune and studying Triton in detail. Such a mission has been proposed several times, but none has yet been approved. Until a spacecraft returns to this distant world, many of Triton's secrets will remain hidden beneath its frozen surface. What we do know, however, is already remarkable. A moon once believed to be a lifeless, frozen sphere has turned out to be a dynamic world with erupting nitrogen geysers, shifting ice plains, and mysterious geological formations. In the darkness of the outer solar system, nearly 5 billion kilometers from the Sun, Triton continues to challenge our understanding of how planets and moons evolve. Its frozen volcanoes are proof that even in the coldest corners of the solar system, geological activity can still thrive. Beyond the strange plumes and frozen volcanoes observed by Voyager 2, Triton's surface contains an extraordinary variety of geological features that reveal a long and complex history. Each region of the Moon tells a story about the forces that have shaped this distant world over billions of years. One of the most fascinating aspects of Triton's landscape is the diversity of its terrain. Unlike many icy moons that appear relatively uniform, Triton displays a patchwork of different geological environments. Some regions are smooth and almost completely free of impact craters, suggesting they were resurfaced relatively recently. Other areas contain ridges, depressions, and strange patterns carved into the ice. This diversity suggests that Triton has experienced multiple phases of geological activity. Among the most striking regions discovered by Voyager 2 are the vast nitrogen ice plains that cover large portions of the Moon's surface. These plains appear remarkably smooth in the spacecraft images, with very few visible craters. In planetary science, a surface with few craters usually indicates that it has been reshaped or resurfaced in the recent geological past. On Triton, the resurfacing process likely involves a combination of cryovolcanism and the slow movement of ice across the surface. Nitrogen ice behaves differently from water ice under the conditions found on Triton. At extremely low temperatures, nitrogen ice can flow slowly over long periods of time, somewhat like glaciers on Earth. Although the motion is extremely slow, it can gradually reshape the landscape. Over thousands or millions of years, flowing nitrogen ice may smooth out older terrain and bury impact craters beneath new layers of frozen material. The result is a landscape that appears surprisingly young, despite the Moon's ancient origin. Another remarkable feature on Triton is the presence of large ridges and valleys stretching across the surface. Some of these ridges run for hundreds of kilometers and form networks of intersecting lines across the icy plains. These structures may have formed when Triton's crust experienced stretching and cracking. If the interior of the Moon once contained large amounts of heat, perhaps generated during its capture by Neptune, the outer shell may have expanded slightly as the interior warmed. This expansion could have fractured the crust, creating long cracks and ridges similar to those seen on Jupiter's moon Europa. Over time, cryovolcanic material may have risen through some of these cracks, depositing fresh ice along their edges. One particularly unusual type of terrain found on Triton is known as cantaloupe terrain. This region contains a pattern of rounded depressions separated by low ridges, giving the surface a texture similar to the skin of a cantaloupe melon. Each depression measures roughly 30 to 40 kilometers across and appears remarkably uniform in size. The origin of this terrain remains one of the most puzzling mysteries on Triton. One theory suggests that these depressions formed when pockets of warmer, less dense ice rose slowly toward the surface from deeper layers. As these rising blobs pushed upward, they may have created gentle domes and valleys in the surface ice. Another possibility is that the terrain formed through convection within the icy crust. In this scenario, warmer ice deep below the surface slowly rises while cooler ice sinks downward. This movement could produce patterns similar to the cantaloupe-like structures observed by Voyager. Regardless of how it formed, the cantaloupe terrain provides strong evidence that Triton's interior was once warm enough to allow ice to flow and move beneath the surface. This internal activity may have been driven by tidal heating. When Triton was first captured by Neptune billions of years ago, its orbit around the planet was likely extremely unstable. Instead of the nearly circular orbit it has today, Triton probably traveled along an elongated path around Neptune. As the Moon moved closer to and farther from Neptune during each orbit, gravitational forces would have stretched and compressed Triton's interior. This constant flexing of the Moon would generate heat, similar to how bending a piece of metal repeatedly causes it to warm. The process is known as tidal heating. Tidal heating plays an important role on several other moons in the solar system. For example, Jupiter's moon Io experiences intense tidal heating that drives the most powerful volcanic activity known anywhere in the solar system. On Triton, tidal heating during the early stages of its capture could have melted large portions of the interior ice. If this happened, Triton may once have possessed a deep subsurface ocean beneath its frozen crust. Over time, as Triton's orbit stabilized, the tidal forces would gradually weaken. The interior would slowly cool, and much of the ocean might eventually refreeze. But some internal heat could remain trapped beneath the surface even today. If pockets of liquid water or slushy ice still exist deep within Triton, they might occasionally rise toward the surface through fractures in the crust. This process could create cryovolcanic eruptions, similar to those observed by Voyager 2. Such eruptions would deposit fresh ice across the surface, helping explain the relatively young appearance of some regions on the Moon. Another intriguing feature discovered on Triton is the presence of dark streaks stretching across the icy plains. These streaks are believed to form when cryovolcanic plumes eject dark particles high into the atmosphere. Winds then carry the particles sideways before they settle back onto the surface. Some streaks extend for more than 150 kilometers. Their orientation suggests that winds in Triton's thin atmosphere blow consistently in a particular direction across the surface. Although Triton's atmosphere is extremely thin, it still plays a significant role in shaping the Moon's surface. The atmosphere consists mainly of nitrogen gas, with small amounts of methane and carbon monoxide. It forms when nitrogen ice on the surface sublimates under the weak sunlight that reaches Neptune's orbit. During Triton's seasonal cycle, nitrogen ice can evaporate from one hemisphere and condense onto the other. This process creates a slow exchange between the atmosphere and the surface. As nitrogen gas moves across the Moon, it can transport fine dust particles and create subtle winds that reshape the landscape over time. Despite its faint atmosphere, Triton even possesses thin layers of clouds composed of nitrogen ice crystals. Voyager 2 captured images of these delicate clouds drifting through the Moon's sky. This discovery further demonstrated that Triton is far more dynamic than scientists once believed. Yet perhaps the most remarkable aspect of Triton's geology is how little we have actually seen. During its brief flyby, Voyager 2 was able to photograph only about 40% of Triton's surface. The remaining regions lie on the far side of the Moon, hidden from the spacecraft's cameras during its encounter. Those unexplored regions could contain entirely new types of terrain or additional cryovolcanic systems. Scientists have long hoped that a future mission might return to Neptune and conduct a detailed survey of Triton. An orbiter equipped with advanced cameras and scientific instruments could map the entire surface, analyze the composition of the ice, and search for signs of internal oceans. Such a mission could also observe cryovolcanic activity over time, revealing how frequently Triton's frozen volcanoes erupt. Understanding these processes would help scientists learn not only about Triton, but also about other icy worlds throughout the solar system. Moons like Europa, Enceladus, and Pluto's moon Charon may share similar geological processes involving frozen materials and subsurface oceans. By studying Triton, scientists may gain insights into how these distant icy worlds evolve over billions of years. In the dark outskirts of the solar system, Triton stands as one of the most mysterious moons ever discovered. Its frozen volcanoes, strange terrain, and hidden internal processes reveal a world that is anything but static. Beneath the quiet surface of nitrogen ice, powerful forces continue shaping this distant moon, reminding us that even the coldest worlds can still be alive with geological activity. Although Triton appears quiet and frozen from a distance, its strange geology tells a story of powerful forces that have shaped the moon over billions of years. To understand why Triton possesses frozen volcanoes and unusual terrain, scientists must look not only at its surface, but also deep into its past. The origin of Triton is one of the most unusual stories among the moons of the solar system, and that history may explain many of the geological mysteries we observe today. Unlike most large moons, Triton likely did not form around the planet it orbits today. The major moons of Jupiter, Saturn, and Uranus were probably born from disks of gas and dust that surrounded their planets during the early stages of the solar system. These moons orbit in the same direction that their planets rotate, following stable paths that have existed for billions of years. Triton, however, behaves very differently. It travels around Neptune in a retrograde orbit, meaning it moves in the opposite direction of the planet's rotation. This is extremely unusual. Among large moons in the solar system, Triton is the only one known to follow such an orbit. This odd motion provides an important clue about Triton's origin. Scientists believe Triton was once an independent object in the outer solar system, possibly a dwarf planet similar to Pluto. It likely formed within the distant region known as the Kuiper Belt, a vast disk of icy bodies that extends far beyond the orbit of Neptune. Objects in the Kuiper belt are remnants from the early solar system. They formed from the same material that created the planets, but never combined into a single large body. Instead, they remain scattered across billions of kilometers of space. At some point early in the history of the solar system, Triton may have drifted close to Neptune. Exactly how Neptune captured Triton is still debated, but the most widely accepted explanation involves a gravitational interaction between Triton and another object. One theory suggests that Triton was once part of a binary system, two large objects orbiting each other. When this pair passed near Neptune, the planet's strong gravity disrupted the system. One object was ejected into space, while Triton lost energy and became trapped in orbit around Neptune. Such gravitational exchanges can occur in crowded regions of space, and similar processes may explain how other irregular moons were captured by the giant planets. However, Triton is far larger than most captured moons, which makes its capture even more dramatic. Once Triton became bound to Neptune's gravity, its orbit would not have been stable. Instead of the nearly circular orbit it has today, Triton probably followed a highly elongated path around the planet. Each time Triton passed close to Neptune, powerful tidal forces would stretch and compress the moon's interior. These forces generate heat through friction within the moon's structure. The process is similar to repeatedly bending a metal wire until it becomes warm. This tidal heating could have dramatically transformed Triton's interior. Large portions of the moon's icy interior may have melted, creating layers of liquid water mixed with ammonia and other chemicals that act as antifreeze. Such mixtures remain liquid at temperatures far below the freezing point of pure water. If Triton once possessed a global subsurface ocean, it would have been hidden beneath a thick shell of ice. At the same time, tidal forces may have triggered intense geological activity across the moon's surface. Ice could have flowed like lava, reshaping the terrain and covering older impact craters. Cryovolcanic eruptions may have carried slushy mixtures of water, ammonia, and other compounds upward from deep underground. These eruptions would gradually resurface the moon. Over millions of years, Triton's orbit slowly changed. Gravitational interactions between Triton and Neptune caused the orbit to shrink and become more circular. As this process continued, the tidal forces weakened. Eventually, the intense heating inside Triton would have declined. The interior began to cool, and any subsurface ocean may have started freezing again. However, the geological scars left behind by this early activity remain visible on Triton's surface today. The relatively small number of impact craters across much of the moon suggests that its surface was resurfaced long after the early bombardment period of the solar system. In planetary science, surfaces that lack many craters are usually considered young in geological terms. This makes Triton one of the youngest surfaces observed among the large moons in the outer solar system. Another important factor influencing Triton's geology is its axial tilt. Triton's axis is tilted by roughly 157 degrees, meaning the moon is effectively rotating almost upside down compared with many other moons. This extreme tilt creates unusual seasonal patterns. Each pole of Triton experiences decades of continuous sunlight, followed by decades of darkness. During the long summer season, sunlight slowly warms the surface ice. Although the sunlight at Neptune's distance is extremely weak, it can still cause nitrogen ice to sublimate into gas. This seasonal heating plays an important role in powering the cryovolcanic plumes observed by Voyager 2. When sunlight penetrates the surface layers of nitrogen ice, it can warm the ice trapped beneath a translucent upper layer. Gas builds up below the surface until pressure forces it to erupt through cracks. These eruptions create the tall plumes and dark streaks seen in the spacecraft images. Seasonal changes may also cause large amounts of nitrogen ice to migrate from one hemisphere to another. As nitrogen gas rises into the atmosphere, it may travel across the Moon before freezing again in colder regions. Over decades or centuries, this process gradually redistributes ice across Triton's surface. The result is a constantly evolving landscape, shaped by both geological and atmospheric forces. Another mystery scientists continue to investigate is the possibility that Triton still contains internal heat today. Although tidal heating would have decreased after Triton's orbit stabilized, other sources of heat may remain. One of these sources is radioactive decay. Deep within Triton's rocky core, radioactive elements slowly release heat as they decay over billions of years. This heat could help maintain pockets of liquid water beneath the ice. If such pockets exist, they might occasionally reach the surface through fractures in the crust, triggering cryovolcanic eruptions. This possibility places Triton among a growing class of icy bodies known as ocean worlds. Ocean worlds are planetary bodies that may contain liquid water oceans beneath their icy shells. Jupiter's moon, Europa, and Saturn's moon Enceladus are well-known examples. These hidden oceans have become major targets in the search for environments where life might potentially exist beyond Earth. Although Triton lies much farther from the Sun than Europa or Enceladus, the presence of antifreeze compounds such as ammonia could allow liquid water to exist beneath its surface, even at extremely low temperatures. If Triton does possess a subsurface ocean, it would raise fascinating questions about the Moon's long-term evolution. Could internal heat still drive geological activity beneath the crust? Could cryovolcanic eruptions transport material from the ocean to the surface? And could chemical reactions within that hidden ocean create conditions suitable for simple forms of life? For now, these questions remain unanswered. The Voyager 2 flyby provided only a brief glimpse of Triton's complex world. The spacecraft passed the Moon at high speed, capturing images and data during only a few hours of observation. Yet even that short encounter revealed a Moon far more dynamic and mysterious than anyone had expected. Future missions to the outer solar system may one day return to Triton and explore it in far greater detail. An orbiter around Neptune could map the entire surface of Triton, study its atmosphere, and search for evidence of subsurface oceans or active cryovolcanoes. Such a mission could transform our understanding of this distant moon. Until that day arrives, Triton remains one of the most intriguing and least understood worlds in the solar system. Its frozen volcanoes, unusual origin, and mysterious interior hint at a complex history shaped by gravity, ice, and time. And somewhere beneath its pale surface of nitrogen frost, the forces that created those frozen eruptions may still be at work. As scientists continued studying the strange geology of Triton, it became increasingly clear that the Moon represents one of the most unusual environments in the solar system. Its frozen volcanoes, moving nitrogen ice, and mysterious terrain suggest that powerful processes continue shaping the surface, even in the extreme cold of the outer solar system. One of the most intriguing aspects of Triton's activity is how closely it is tied to the behavior of nitrogen ice. On Earth, nitrogen exists almost entirely as a gas in the atmosphere, but on Triton, where temperatures are incredibly low, nitrogen freezes into solid ice that covers large areas of the Moon's surface. In some places, this ice may form layers several meters thick. Unlike water ice, which remains relatively stable at low temperatures, nitrogen ice can change phase more easily. Even the faint sunlight that reaches Neptune's orbit can warm nitrogen ice enough to cause sublimation, the process where a solid turns directly into gas. This transformation is central to many of Triton's surface processes. During Triton's long summer seasons, sunlight gradually warms parts of the surface. When nitrogen ice begins to sublimate, it forms gas trapped beneath the surface layers of translucent ice. As the gas accumulates, pressure builds until the surface fractures. When the trapped gas escapes, it bursts upward through the ice, carrying fine dust and dark particles into the atmosphere. These eruptions create the cryovolcanic plumes that Voyager 2 observed, rising above Triton's surface. But the story does not end with the eruption itself. Once the material is ejected into the atmosphere, Triton's thin winds begin to shape its distribution across the surface. Although the Moon's atmosphere is extremely faint compared with Earth's, it still contains enough gas to transport particles over large distances. The winds carry the dark dust sideways across the icy plains before the particles settle back onto the surface. This process creates the long, dark streaks that stretch across Triton's landscape. Some of these streaks extend for more than 100 kilometers, indicating that winds can move material over remarkable distances. These streaks provide valuable clues about the direction of atmospheric circulation on Triton. By analyzing their orientation, scientists concluded that winds in Triton's atmosphere tend to blow consistently in a particular direction across the surface. This suggests that seasonal temperature differences between regions may drive atmospheric motion. The interaction between cryovolcanic eruptions and atmospheric winds creates a constantly changing surface environment. Over time, repeated eruptions deposit fresh layers of material, while winds redistribute dust across the frozen plains. These processes may gradually alter the appearance of the Moon's surface. In addition to nitrogen ice, Triton's surface contains several other frozen compounds. Methane ice is present in small quantities and contributes to the Moon's pale coloration. Carbon monoxide ice has also been detected, along with traces of more complex organic molecule formed by chemical reactions driven by radiation from the Sun and Neptune's magnetosphere. These materials may play a role in shaping Triton's geology. When exposed to radiation, methane molecules can break apart and recombine to form darker organic compounds known as tholins. These compounds are believed to be responsible for the reddish or brownish coloration seen on many icy bodies in the outer solar system. On Triton, small amounts of these darker materials may mix with the nitrogen ice, forming the dust particles carried by cryovolcanic plumes. Over time, these deposits may gradually darken portions of the surface. The presence of different types of ice also influences the mechanical properties of Triton's crust. Water ice forms a strong, rigid structure that behaves somewhat like rock at extremely low temperatures. Nitrogen ice, on the other hand, is much softer and can flow more easily over long time scales. This difference may create layered structures within Triton's crust. A stronger shell of water ice could lie beneath a thinner layer of nitrogen ice that moves more easily across the surface. Such layering may help explain why some regions of Triton appear smooth, while others contain ridges and fractures. Another factor affecting Triton's surface is the constant bombardment by radiation and charged particles trapped in Neptune's magnetic field. Neptune possesses a powerful magnetosphere that extends far into space and interacts with the surfaces of its moons. Charged particles traveling along magnetic field lines can strike Triton's surface, breaking apart molecules in the ice. These interactions can gradually alter the chemical composition of the surface layers. Over long periods of time, radiation may produce new compounds that darken the ice or change its reflectivity. This radiation-driven chemistry is thought to occur on many icy moons in the outer solar system. On Triton, it may contribute to the formation of the dark materials seen in the cryovolcanic plumes. Despite these complex processes, Triton remains one of the least explored worlds in the solar system. The Voyager 2 flyby provided only a brief look at the moon's surface, capturing images of just under half of the moon. The remaining regions remain largely unknown. Even within the areas that were photographed, the resolution of the images was limited compared with what modern spacecraft could achieve. If a new mission were sent to Neptune, scientists could map Triton's entire surface in high detail. Such observations might reveal additional cryovolcanoes, new types of terrain, or even evidence of ongoing geological activity. A spacecraft orbiting Neptune could also study Triton's atmosphere over time, observing seasonal changes in the distribution of nitrogen gas and ice. These measurements would help scientists understand how Triton's atmosphere interacts with the surface and drives the formation of cryovolcanic plumes. Perhaps the most exciting possibility is that a future mission could search for signs of a subsurface ocean beneath Triton's icy crust. If such an ocean exists, it would make Triton part of a growing group of ocean worlds in the outer solar system. These worlds are of great interest to scientists because liquid water is considered one of the key ingredients necessary for life as we know it. Although Triton lies far from the warmth of the sun, internal heat sources could potentially maintain pockets of liquid water beneath the ice. Chemical reactions between water and rock in the moon's interior might provide energy that could support microbial life in such environments. While there is currently no direct evidence that life exists on Triton, the possibility makes the moon an intriguing target for future exploration. Even without life, Triton offers a remarkable opportunity to study how geology can operate under conditions vastly different from those found on Earth. Its frozen volcanoes demonstrate that geological activity does not always require molten rock or high temperatures. Instead, ice, gas, and pressure can combine to create entirely new types of volcanic processes. In the distant reaches of the solar system, Triton continues to challenge scientists' understanding of how planetary bodies evolve. What once seemed like a quiet, frozen moon has turned out to be a dynamic world shaped by ice, gas, and hidden forces beneath its surface. And, until another spacecraft returns to explore it more closely, many of Triton's secrets will remain locked beneath its frozen crust. As scientists continued studying the data returned by Voyager 2, another fascinating aspect of Triton began to emerge. The moon is not only shaped by geological forces beneath the surface, but also by an active interaction between its surface and its atmosphere. Although Triton's atmosphere is extremely thin compared with Earth's, it plays a surprisingly important role in shaping the moon's environment. Triton's atmosphere is composed primarily of nitrogen gas, the same gas that dominates Earth's atmosphere. However, the density of Triton's atmosphere is incredibly small, roughly 100,000 times thinner than Earth's atmosphere at sea level. To human observers, this atmosphere would feel almost like a vacuum. Yet even such a delicate atmosphere can drive remarkable processes across the moon's surface. The atmosphere forms through a continuous exchange between frozen nitrogen on the surface and nitrogen gas in the air above it. When sunlight reaches Triton's icy plains, it warms the surface just enough to cause nitrogen ice to sublimate, transforming directly from solid ice into gas. As the nitrogen gas rises from the surface, it creates a thin atmospheric layer surrounding the moon. But Triton's extreme seasons play a crucial role in this process. Because Triton's axis is tilted dramatically, almost completely upside down compared with most moons, its poles experience extremely long seasons. Each pole can face the sun continuously for decades, followed by decades of darkness. During the long summer season, sunlight slowly warms the nitrogen ice covering that hemisphere. Over time, vast quantities of nitrogen ice may sublimate and enter the atmosphere. When the seasons change, the opposite hemisphere cools, and the nitrogen gas begins to freeze again, forming fresh layers of ice. This slow migration of nitrogen between hemispheres creates seasonal cycles that may last for hundreds of years. These cycles gradually reshape Triton's surface. As nitrogen ice accumulates in certain regions, it may form thick deposits that bury older terrain beneath fresh layers of frost. In other regions, sublimation may expose darker material lying beneath the ice. These changes may explain why some areas of Triton appear brighter or darker than others. The seasonal redistribution of nitrogen also affects the moon's atmosphere. As nitrogen gas rises from warm regions and moves toward colder areas, it creates gentle winds across the surface. Although these winds are extremely weak compared with those on Earth, they are strong enough to move tiny dust particles across the frozen landscape. This atmospheric circulation is closely linked to the dark streaks observed on Triton's surface. When cryovolcanic plumes erupt, they release dark particles along with nitrogen gas. Once these particles fall back toward the surface, winds carry them across the ice plains, forming long streaks that stretch for tens or even hundreds of kilometers. By studying the direction and shape of these streaks, scientists were able to estimate the speed of Triton's winds. The winds appear to move at speeds of roughly 5 to 15 meters per second, which is remarkable for such a thin atmosphere. These winds may also influence the behavior of cryovolcanic plumes themselves. As nitrogen gas erupts from beneath the surface, it rises vertically for several kilometers before encountering horizontal winds in the upper atmosphere. These winds then bend the plume sideways, causing the material to spread across the surface in a specific direction. The result is a dramatic plume that curves through the sky before depositing its material on the frozen ground. Voyager 2 captured images of several active plumes during its flyby. Some plumes appeared to reach heights of nearly 8 kilometers before being blown sideways by the winds. These eruptions are among the most distant volcanic events ever observed in the solar system. Another remarkable discovery made during the Voyager mission was the presence of clouds in Triton's atmosphere. These clouds are extremely thin and composed of tiny nitrogen ice crystals. They form when nitrogen gas in the atmosphere cools and condenses into microscopic particles. The clouds float gently above the moon's surface, creating faint wisps that drift through the sky. Although they are difficult to see, these clouds provide additional evidence that Triton's atmosphere is constantly changing. The presence of clouds also suggests that weather-like processes may occur on Triton, albeit on a very slow and subtle scale. Changes in temperature, atmospheric pressure, and sunlight could influence the formation and movement of clouds over time. These processes make Triton one of the few moons in the solar system known to possess an atmosphere capable of producing cloud formation. But Triton's atmosphere is not shaped only by the sun. The moon also interacts with the powerful magnetic environment surrounding Neptune. Neptune possesses a large and complex magnetosphere that traps charged particles from the solar wind. These particles travel along magnetic field lines and occasionally collide with the surfaces of the planet's moons. When charged particles strike Triton's icy surface, they can break apart molecules within the ice. This process, known as radiolysis, alters the chemical composition of the surface layers. For example, methane molecules exposed to radiation can break apart and recombine into more complex organic compounds. These compounds often appear darker than the surrounding ice. Over long periods of time, radiation may gradually darken portions of Triton's surface. This process may help explain the origin of the dark particles observed in cryovolcanic plumes. Radiation-driven chemistry may produce the dark organic material that becomes trapped within the nitrogen ice layers. When eruptions occur, these particles are carried upward into the plumes and later deposited across the surface. Another consequence of radiation exposure is the gradual loss of atmosphere. Some nitrogen molecules in Triton's atmosphere gain enough energy from sunlight or charged particles to escape the moon's gravity entirely. Over time, this process slowly removes gas from the atmosphere and releases it into space. However, this loss is balanced by the continuous sublimation of nitrogen ice from the surface. As long as frozen nitrogen remains on Triton's surface, the atmosphere can replenish itself through sublimation during warmer seasons. This balance between atmospheric loss and surface sublimation creates a delicate equilibrium that has likely persisted for millions of years. Despite its faint atmosphere and extreme cold, Triton demonstrates that even distant icy worlds can possess complex interactions between their surfaces, atmospheres, and internal structures. These interactions create a dynamic environment that continues to evolve over time. The frozen volcanoes of Triton are only one part of this larger system. Beneath the surface, hidden processes may still be shaping the moon's interior. Above the surface, Atmospheric winds and seasonal cycles gradually reshaped the icy plains. Together, these forces transformed Triton into a living geological system rather than a frozen relic of the early solar system. Yet, our understanding of Triton remains incomplete. The Voyager 2 spacecraft provided only a brief snapshot of the Moon's activity during a single moment in time. Many of the processes scientists suspect may occur on Triton have never been observed directly. Future missions to Neptune could dramatically expand our knowledge of this mysterious world. An orbiter equipped with modern instruments could monitor Triton's plumes over time, map seasonal changes across the surface, and search for evidence of subsurface oceans beneath the crust. Such discoveries could reveal whether Triton still contains hidden reservoirs of liquid water, and whether cryovolcanism continues to reshape its surface today. Until that day arrives, Triton remains one of the most intriguing and mysterious moons in the outer solar system. Its frozen volcanoes, thin atmosphere, and shifting ice landscapes remind us that even the coldest worlds can possess extraordinary complexity, and somewhere beneath its pale nitrogen frost, the forces that power those distant eruptions may still be quietly at work. Far beneath Triton's frozen surface lies one of the most intriguing questions scientists continue to debate. What is happening inside the Moon today? While Voyager 2 revealed a surprisingly active surface, the spacecraft could only provide limited information about Triton's interior. Yet many of the geological features observed suggest that important processes may still be occurring deep below the ice. To understand Triton's interior, scientists begin by considering the basic structure of icy moons. Most large icy bodies in the outer solar system are thought to contain several distinct layers. At the center lies a rocky core composed of silicate minerals and heavier elements. Surrounding this core is a thick mantle of water ice mixed with other frozen compounds. Above that lies the outer crust, which forms the visible surface of the Moon. In Triton's case, the structure may be slightly more complex. The Moon is believed to consist of roughly 2/3 rock and 1/3 ice, making it relatively dense compared with many other icy moons. This suggests that Triton contains a significant rocky interior capable of producing heat through radioactive decay. Radioactive elements such as uranium, thorium, and potassium naturally release heat as they slowly decay over billions of years. This process occurs deep inside many planetary bodies, including Earth. Although the heat generated by radioactive decay is modest compared with other energy sources, it can play an important role in maintaining internal warmth over long periods of time. Inside Triton, this heat may help prevent the complete freezing of deeper layers. Combined with the tidal heating that likely occurred during Triton's early capture by Neptune, radioactive heating could have melted portions of the icy mantle. This raises the possibility that Triton once possessed a subsurface ocean beneath its outer crust. Such oceans are now known to exist on several moons in the outer solar system. Jupiter's moon, Europa, and Saturn's moon Enceladus both contain liquid water oceans beneath thick shells of ice. These hidden oceans remain liquid because of internal heating and the presence of substances such as ammonia that lower the freezing point of water. If Triton once contained a similar ocean, it may have formed during the intense tidal heating phase, that followed the moon's capture by Neptune. As Triton's orbit gradually stabilized, the tidal heating would have declined, allowing the interior to cool. Over time, much of the ocean may have frozen again, forming thick layers of ice above and below the remaining liquid. But some scientists believe that pockets of liquid water may still exist today. The presence of ammonia mixed with water could allow the liquid to remain stable at extremely low temperatures. Ammonia acts as a natural antifreeze, lowering the freezing point of water and making it easier for liquid layers to persist beneath the crust. If such liquid reservoirs remain inside Triton, they could occasionally find pathways to the surface. Fractures in the icy crust might allow slushy mixtures of water, ammonia, and other compounds to rise upward through the ice. When this material reaches the surface, it could erupt as cryovolcanic flows or geysers. Although the plumes observed by Voyager 2 appear to be driven primarily by nitrogen gas, deeper cryovolcanic processes may also occur beneath the surface. Evidence for this possibility can be found in some of Triton's unusual surface features. In several regions, scientists have identified smooth plains that appear to have flowed across the landscape like frozen lava. These plains cover older terrain and filled depressions, suggesting that liquid or semi-liquid material once moved across the surface. The material responsible for these flows may have been composed of water ice mixed with ammonia and other volatile substances. When such mixtures erupt onto the surface, they can spread out before freezing again in the extreme cold. Over time, repeated eruptions could create extensive cryovolcanic plains, similar to the lava plains found on volcanic worlds like Io or Venus. Another intriguing possibility is that Triton's interior still experiences slow convection. Convection occurs when warmer material rises while cooler material sinks. In planetary interiors, this process can occur within layers of ice or rock if the temperature difference between deep and shallow layers becomes large enough. If Triton's interior still contains warm ice beneath a colder outer crust, convection could gradually transport heat toward the surface. This slow circulation might help explain the formation of some of Triton's unusual terrain patterns, including the cantaloupe-like depressions observed in certain regions. In such a scenario, warmer pockets of ice rising toward the surface could create gentle domes or depressions in the crust. Over millions of years, convection could slowly reshape large portions of the moon's surface. However, determining whether convection still occurs inside Triton requires more detailed observations than Voyager 2 was able to provide. Another clue about Triton's interior may come from the moon's overall shape and gravitational behavior. If Triton once possessed a global subsurface ocean, the presence of liquid water beneath the crust would have influenced the moon's rotation and tidal interactions with Neptune. In some icy moons, subsurface oceans create slight variations in the gravitational field that can be detected by spacecraft. Future missions to Triton could use sensitive instruments to measure these variations and determine whether a liquid layer still exists beneath the ice. The existence of such an ocean would have important implications for the moon's long-term geological activity. Liquid reservoirs beneath the surface could supply material for cryovolcanic eruptions and help maintain internal heat. Even small pockets of liquid could produce enough pressure to fracture the crust and drive eruptions. Beyond its geological significance, a subsurface ocean would also raise intriguing questions about the potential for life. On Earth, life exists in some of the most extreme environments imaginable, including deep beneath the ocean floor, where sunlight never reaches. In these environments, microorganisms survive by using chemical energy rather than sunlight. If Triton possesses a subsurface ocean containing liquid water and chemical compounds, it could potentially provide similar environments. Chemical reactions between water and rock in the Moon's interior might produce energy sources that microorganisms could use. Although Triton is extremely cold at the surface, conditions deep beneath the ice might be far more stable. Of course, there is currently no evidence that life exists on Triton, but the possibility makes the Moon an intriguing candidate for future exploration. In recent years, scientists have become increasingly interested in exploring ocean worlds throughout the solar system. Missions are already being planned to study Europa and Enceladus more closely, searching for signs of subsurface oceans and potential habitability. Triton may eventually join this list of exploration targets. A spacecraft orbiting Neptune could perform detailed measurements of Triton's gravity, magnetic environment, and surface composition. These observations could reveal whether a hidden ocean still exists beneath the crust. Such a mission could also monitor cryovolcanic plumes over time, searching for evidence that deeper eruptions occasionally reach the surface. If future spacecraft detect water vapor or other materials associated with subsurface reservoirs, it would dramatically transform our understanding of this distant moon. For now, however, Triton remains largely unexplored. The single flyby of Voyager 2 provided only a brief glimpse of its complex world. Yet even that short encounter revealed a moon unlike any other. Its frozen volcanoes, strange terrain, and possible hidden ocean hint at a dynamic interior still capable of shaping the surface today. Far beyond the warmth of the sun, Triton continues to challenge our assumptions about where geological activity can occur. And deep beneath its icy crust, the forces that once created its frozen volcanoes may still be quietly at work. As scientists studied Triton more closely, they began to realize that the moon does not simply represent an unusual world in Neptune's system. Instead, Triton may provide important clues about the entire outer solar system and the evolution of icy bodies beyond the orbit of Neptune. Many of the features observed on Triton closely resemble those found on other distant objects, particularly dwarf planets and Kuiper Belt objects. This similarity is not a coincidence, because Triton was most likely captured from the Kuiper Belt. It may actually be more closely related to dwarf planets such as Pluto than to the regular moons of Neptune. In many ways, Triton can be thought of as a captured dwarf planet that now happens to orbit Neptune. This origin helps explain several unusual aspects of the moon. For example, Triton's density, composition, and surface chemistry are very similar to those observed on Pluto. Both worlds contain large amounts of nitrogen ice, methane ice, and carbon monoxide ice. These substances form the bright, reflective surfaces seen in telescope images. Both bodies also show evidence of active surface processes involving these volatile ices. When the New Horizons spacecraft flew past Pluto, in 2015. It revealed a world that was far more geologically complex than scientists had expected. Pluto possesses vast plains of nitrogen ice that slowly flow across its surface, reshaping the landscape over time. One region on Pluto, known as Sputnik Planitia, is a massive basin filled with nitrogen ice that behaves almost like a slow-moving glacier. Within this basin, convection cells slowly circulate the ice, creating polygon-shaped patterns across the surface. Although Triton has not been explored in the same level of detail as Pluto, many scientists suspect that similar processes may occur there. The nitrogen ice plains on Triton could behave in ways very similar to those seen on Pluto, slowly moving and resurfacing the landscape over long periods of time. If this is true, Triton may represent one of the best opportunities to study the geology of Kuiper belt-type objects without traveling all the way to the distant outer reaches of the solar system. Another important similarity between Triton and Pluto is the presence of volatile cycles involving nitrogen ice. On both worlds, nitrogen exists in a delicate balance between solid ice on the surface and gas in the atmosphere. Seasonal changes cause nitrogen to sublimate into the atmosphere and later freeze again onto the surface. These cycles can redistribute large amounts of ice across the planet or moon. On Pluto, scientists have observed glaciers of nitrogen ice flowing slowly across the landscape. On Triton, the same type of flow may occur on the smooth plains observed by Voyager 2. Over millions of years, these slow movements can reshape large regions of the surface. The study of Triton, therefore, provides valuable insights into the behavior of volatile ices throughout the outer solar system. But Triton is not only important for understanding dwarf planets. Its frozen volcanoes represent a unique form of geological activity that may occur on many icy bodies. Cryovolcanism has now been observed or suspected on several moons, including Europa, Enceladus, and possibly Titan. On Europa, plumes of water vapor may erupt from beneath the icy crust, driven by the pressure of a global ocean hidden below the surface. On Enceladus, powerful jets of water vapor and ice particles erupt from fractures near the South Pole. These eruptions feed a ring of material around Saturn and provide strong evidence for a subsurface ocean. Triton's cryovolcanic plumes appear to operate differently. Instead of being driven primarily by water vapor from a subsurface ocean, the plumes on Triton seem to be powered mainly by nitrogen gas trapped beneath surface ice. This makes Triton an important example of a solar-driven cryovolcanic system, where sunlight plays a key role in triggering eruptions. Understanding how these plumes operate may help scientists identify similar processes on other icy worlds. The more researchers study Triton, the more they realize that frozen worlds can be surprisingly dynamic. In the past, many scientists believed that geological activity required large amounts of internal heat. Worlds located far from the sun were assumed to be frozen relics with little or no activity. But discoveries on Triton, Pluto, and other icy bodies have completely changed this view. Instead of being static and lifeless, many distant objects appear to be evolving through complex interactions between ice, atmosphere, radiation, and internal heat. These discoveries have expanded our understanding of planetary geology. On Earth, volcanic activity is driven by molten rock, but on Triton and other icy worlds, completely different materials, such as nitrogen, methane, or water ice, can behave like flowing fluids under the right conditions. These substances can erupt, flow, and reshape the landscape in ways that resemble volcanic activity on rocky planets. Triton, therefore, represents an entirely different category of geological world. It is a place where ice behaves like lava, where gas erupts through frozen crusts, and where sunlight can trigger eruptions in one of the coldest environments in the solar system. Another reason Triton is so scientifically valuable is that it may represent a transitional object between dwarf planets and moons. Most large moons formed around their planets, but Triton likely originated elsewhere before being captured by Neptune's gravity. This means Triton preserves characteristics of both types of objects. By studying Triton, scientists may learn more about the early migration of planets and the chaotic processes that shaped the solar system billions of years ago. During the early history of the solar system, the giant planets likely moved through the outer regions, scattering smaller bodies and altering their orbits. These migrations may have led to events such as Triton's capture by Neptune. Understanding this process could reveal how common captured worlds might be around other planets. If Triton represents a captured dwarf planet, there may have once been many similar objects in the early solar system. Another mystery scientists hope to solve involves Triton's future evolution. Although Triton currently follows a stable orbit around Neptune, tidal interactions between the Moon and the planet continue to occur. Over extremely long periods of time, these interactions slowly alter Triton's orbit. Current models suggest that Triton's orbit is gradually shrinking. If this process continues for billions of years, Triton may eventually move close enough to Neptune to be torn apart by tidal forces. If that happens, the Moon could break apart and form a ring system around Neptune, similar to the rings of Saturn. However, this process would take billions of years and will not occur anytime soon. For now, Triton continues its slow journey around Neptune, carrying with it the geological scars of its violent past. Its frozen volcanoes, flowing nitrogen ice, and mysterious terrain provide a window into processes that operate on some of the most distant worlds in the solar system. Each new discovery about Triton expands our understanding of how icy bodies evolve and interact with their environments. And as scientists continue to analyze the data collected by Voyager 2, they are reminded that this distant moon still holds many secrets waiting to be uncovered. One day, a future spacecraft may return to Neptune and explore Triton in detail. When that mission finally arrives, it may reveal that Triton is even more active and complex than we imagine today. Hidden beneath its pale surface of nitrogen frost may lie a world shaped by ice, gas, and geological forces that continue to operate in the deep darkness of the outer solar system. Even though Triton lies nearly 4.5 billion kilometers from the Sun, it continues to challenge everything scientists once believed about the outer solar system. For decades, researchers assumed that distant icy worlds would be geologically quiet, frozen relics left unchanged since the formation of the solar system. But Triton has revealed a very different reality. Instead of a lifeless surface, Triton shows signs of activity that may still be shaping the Moon today. One of the biggest questions scientists continue to ask is whether the cryovolcanic plumes observed by Voyager 2 are still occurring. The spacecraft witnessed several plumes during its brief flyby in 1989, but because it observed Triton for only a few hours, it remains unknown how frequently these eruptions occur. They could be rare events that happen only under certain seasonal conditions, or they could be part of a much more active system that produces plumes regularly across the Moon's surface. The answer to this question could reveal a great deal about Triton's internal and atmospheric processes. If the plumes occur frequently, it would suggest that the nitrogen-driven cryovolcanic system remains active today. Continuous eruptions would gradually reshape the surface by depositing new material across the landscape. Over long periods of time, this process could cover older terrain and erase impact craters. This may explain why large regions of Triton's surface appear geologically young. Another mystery involves the dark material carried by the plumes. The particles that create Triton's long dark streaks may originate from deeper layers beneath the surface. Some scientists believe that these particles could be organic compounds created by chemical reactions involving methane ice and radiation. When methane molecules are exposed to ultraviolet light from the sun or energetic particles from Neptune's magnetosphere, they can break apart and recombine into complex organic materials known as tholins. Tholins are common across many objects in the outer solar system and are responsible for the reddish coloration seen on bodies such as Pluto and Saturn's moon Titan. On Triton, small amounts of these dark materials may become trapped within nitrogen ice layers beneath the surface. When cryovolcanic eruptions occur, the plumes carry these particles upward into the atmosphere. Winds then distribute them across the surface, creating the streaks visible in spacecraft images. Over time, these deposits may gradually darken parts of Triton's landscape. Understanding the composition of these particles could provide important clues about the chemistry occurring on the Moon. Another key question concerns Triton's internal heat. Although the intense tidal heating that occurred during Triton's capture likely faded long ago, scientists are still trying to determine whether enough heat remains inside the Moon to drive geological activity today. Radioactive decay within Triton's rocky core continues to produce heat, though at a much slower rate than tidal heating once did. If this heat remains trapped beneath thick layers of ice, it could create pockets of warmer material within the interior. These pockets might slowly rise toward the surface through fractures in the crust. Even small amounts of heat could play a role in maintaining subsurface reservoirs of liquid or slushy ice. If such reservoirs exist, they could provide additional sources of material for cryovolcanic eruptions. This possibility connects Triton to a larger group of worlds known as ocean worlds. Ocean worlds are bodies that may contain liquid water beneath their icy surfaces. Europa, Enceladus, and possibly even Pluto may possess hidden oceans beneath their crusts. If Triton also contains a subsurface ocean, it would make the Moon one of the most distant ocean worlds in the solar system. Such oceans are especially interesting because liquid water is considered a key ingredient for life. On Earth, life exists wherever liquid water is present, from deep ocean trenches to underground rock formations kilometers below the surface. In these environments, life often relies not on sunlight, but on chemical energy produced by interactions between water and rock. If similar chemical processes occur inside Triton, they could potentially create environments capable of supporting microbial life. However, confirming the existence of a subsurface ocean on Triton would require new spacecraft missions equipped with advanced instruments. One possible method involves measuring Triton's gravitational field. If a liquid ocean exists beneath the crust, it would affect the way the Moon responds to Neptune's gravity. Subtle variations in Triton's shape and gravitational pull could reveal the presence of liquid layers deep within the interior. Another method would involve studying Triton's magnetic environment. On some moons, subsurface oceans conduct electricity and interact with surrounding magnetic fields. Instruments capable of detecting these interactions could provide indirect evidence of hidden oceans. Future missions might also attempt to observe cryovolcanic plumes directly. If plumes erupt from deeper reservoirs beneath the surface, they may contain traces of materials originating from the Moon's interior. Analyzing these materials could reveal whether liquid water or other compounds exist below the crust. For scientists interested in the search for life beyond Earth, this type of investigation is extremely important. Although Triton lies far from the warmth of the sun, it may still possess environments where life could theoretically survive. Even if no life exists there today, studying Triton could reveal how such environments form and evolve on icy worlds. Beyond its potential for harboring subsurface oceans, Triton also offers insights into the broader history of the solar system. Because Triton likely originated in the Kuiper Belt before being captured by Neptune, the Moon may preserve information about the early conditions of that distant region. Many Kuiper Belt objects remain poorly understood because they are extremely difficult to reach with spacecraft. But Triton effectively brings a Kuiper Belt-type object into orbit around a giant planet where it may eventually be explored in detail. Studying Triton could therefore provide valuable information about the composition and evolution of distant icy bodies. In addition, Triton's capture by Neptune may have dramatically altered the original moon system of the planet. Before Triton arrived, Neptune may have possessed a collection of regular moons similar to those orbiting Jupiter or Saturn. When Triton was captured, its gravitational influence may have disrupted these moons, causing collisions that destroyed many of them. The debris from these collisions may have formed Neptune's current system of small, irregular moons. This violent event would have reshaped Neptune's satellite system and may explain why Triton is now the dominant moon orbiting the planet. Understanding this process could help scientists learn how planetary systems evolve and how captured worlds can alter the structure of entire moon systems. Even after decades of research, Triton remains one of the most mysterious objects in the solar system. Its frozen volcanoes, unusual orbit, and possible subsurface ocean continue to raise new questions about how distant icy worlds function. The brief encounter with Voyager 2 revealed only a fraction of Triton's secrets. Nearly half of the moon's surface has never been photographed in detail. Entire regions remain completely unexplored. One day, a new mission may return to Neptune and finally reveal what lies on the far side of Triton. Such a mission could transform our understanding of cryovolcanism, icy geology, and the hidden oceans that may exist on worlds far beyond the orbit of Earth. Until then, Triton remains a distant and enigmatic world, orbiting silently around Neptune in the cold darkness of the outer solar system. and beneath its frozen crust, the forces that created its strange volcanoes may still be quietly shaping its future. As scientists look back at everything that has been discovered about Triton, it becomes clear that this distant moon represents one of the most fascinating and unexpected worlds in the entire solar system. What once appeared to be a simple frozen satellite orbiting far beyond the warmth of the sun has instead revealed itself to be a dynamic environment shaped by powerful geological, atmospheric, and possibly even internal processes. The frozen volcanoes observed on Triton are among the most striking examples of how unusual planetary activity can become under extreme conditions. On Earth, volcanoes erupt molten rock driven by intense internal heat. On Triton, however, the eruptions are powered by nitrogen gas and frozen compounds trapped beneath layers of ice. These cryovolcanic plumes demonstrate that geological activity does not always require the high temperatures we associate with volcanism on rocky planets. Instead, the combination of sunlight, volatile ices, and pressure beneath the surface can create powerful eruptions, even in one of the coldest environments in the solar system. The discovery of these plumes completely changed how scientists think about icy worlds. Before Voyager 2 visited Neptune, most researchers believed that distant moons would be geologically inactive. Far from the sun, it seemed unlikely that enough energy could exist to drive any kind of surface activity. But Triton proved that this assumption was incorrect. Even in the deep cold of the outer solar system, subtle processes involving frozen gases and seasonal heating can produce dramatic geological phenomena. Triton's frozen volcanoes are only one part of a much larger story. The moon's surface displays evidence of resurfacing, flowing nitrogen ice plains, strange cantaloupe-like terrain, and long dark streaks created by atmospheric winds. Each of these features reflects a complex interaction between the moon's surface, atmosphere, and interior. Together, they reveal a world that continues to evolve, despite its great distance from the sun. The atmosphere of Triton plays an important role in this system. Although extremely thin, the atmosphere allows nitrogen gas to circulate between the surface and the sky. Seasonal cycles cause nitrogen ice to sublimate into gas and later freeze again in colder regions. This exchange gradually redistributes ice across the moon's surface, shaping the landscape over decades and centuries. The winds generated by this atmospheric circulation carry dust from cryovolcanic eruptions across the icy plains, creating the dark streaks that stretch across the surface. In this way, Triton's frozen volcanoes and its atmosphere work together to reshape the moon's terrain. Yet the greatest mysteries of Triton may lie hidden beneath its icy crust. The possibility that Triton once possessed, or may still possess, a subsurface ocean raises fascinating questions about the moon's interior. If liquid water exists beneath the surface, it could represent one of the most distant ocean environments in the solar system. Such oceans are of particular interest because they may provide conditions where life could potentially exist. On Earth, life thrives in deep ocean environments where sunlight never reaches. Microorganisms survive by using chemical energy produced by reactions between water and rock. If similar processes occur inside Triton, it is possible that microscopic life could theoretically exist in hidden pockets beneath the ice. Although this idea remains purely speculative, it highlights the importance of studying icy ocean worlds throughout the solar system. In recent years, scientists have begun focusing more attention on these environments. Missions are being developed to explore Jupiter's moon Europa and Saturn's moon Enceladus, both of which are believed to contain global subsurface oceans. Triton may one day become part of this effort. Because Triton is likely a captured object from the Kuiper Belt, it represents a unique opportunity to study a distant dwarf planet-type world up close. Most Kuiper Belt objects are extremely difficult to reach with spacecraft. Their vast distance from the Sun makes exploration challenging and time-consuming. But Triton effectively brings a Kuiper Belt-like object into orbit around a giant planet, where it could be studied by a spacecraft orbiting Neptune. Such a mission would provide an unprecedented opportunity to explore the geology, chemistry, and internal structure of this mysterious moon. A future Neptune orbiter could map Triton's entire surface in high detail, revealing regions that have never been photographed. It could observe cryovolcanic eruptions in real time and measure seasonal changes in the moon's atmosphere. Instruments designed to study gravity and magnetic fields could search for evidence of subsurface oceans beneath the crust. Other instruments could analyze the composition of surface ice and the particles carried by cryovolcanic plumes. These measurements would provide critical information about how icy worlds evolve over billions of years. They could also reveal whether Triton still contains internal heat capable of driving geological activity today. Beyond its scientific importance, Triton also tells a broader story about the history of the solar system. Its unusual retrograde orbit suggests that it was captured by Neptune early in the solar system's history. This capture event may have dramatically reshaped Neptune's original system of moons. Before Triton arrived, Neptune may have possessed a collection of regular satellites similar to those orbiting other giant planets. When Triton was captured, its gravitational influence may have destabilized these moons, causing collisions that destroyed many of them. The debris from those collisions may have formed Neptune's current system of smaller, irregular moons. If this scenario is correct, Triton's arrival may have permanently altered the architecture of Neptune's satellite system. Understanding this event could help scientists learn more about the chaotic processes that shaped the early solar system. Planetary migration, gravitational captures, and violent collisions likely played major roles in determining the structure of the planetary systems we observe today. Triton is a surviving witness to those ancient events. Despite everything that has been learned from the Voyager 2 flyby, Triton remains largely unexplored. Nearly 60% of its surface has never been seen in detail. Many of its geological processes are still poorly understood. Its interior remains hidden beneath kilometers of frozen ice. The frozen volcanoes that first captured scientists' attention may represent only a small part of Triton's story. Beneath the icy crust, deeper processes may still be shaping the moon in ways we have yet to discover. For now, Triton continues its slow orbit around Neptune, traveling silently through the cold darkness of the outer solar system. At nearly 5 billion kilometers from the Sun, sunlight is faint and the surface remains frozen in extreme cold. Yet beneath that frozen exterior lies a world far more active and mysterious than anyone once imagined. The frozen volcanoes of Triton stand as a reminder that even the most distant and seemingly lifeless worlds can hide extraordinary geological activity. And somewhere beneath those frozen plains of nitrogen ice, the forces that created those distant plumes may still be quietly at work.